Hello and welcome to 5 Minutes of Postgres. My name is Lucas, and today we're going to talk about out-of-range statistics with Postgres, as well as the getActualVariableRange function. We'll start with this blog post by Franck from the Yugabyte team. In this post, Franck talks about how Postgres as well as Yugabyte handle out-of-range statistics. Now for today, we're just going to focus on Postgres. The idea is when a query in Postgres contains a certain value that you're looking for, and that value is out of the range of what Analyze has collected, then Postgres will have special behavior to handle this out-of-range data. The Analyze in Postgres will run periodically and collect table statistics. And it will essentially sample your table and say, what is the typical value we see here? How frequent is it? And such. And it builds, amongst other things, histograms on that. Now, what can happen is if you have new data being inserted after the most recent analyze, you'll essentially have data that's out of sync with the rest of the statistics on the table. And so the idea is that Postgres can detect such situations and will go to the actual table and the actual indexes to determine what query plans to use. And so oftentimes you would see this when you have something like a sequence or a current timestamp and that value keeps increasing. Now, Franck has a test here where he creates a table. He also turns auto vacuum off because we don't want to have automatic analyze happen. We want to do explicit analyze to test that behavior. So he has 3 columns on this table. He has an ID column, a timestamp, and a text column. The initial data here, that's just going to sit on the February 8th timestamp, and it's going to just have one single text value as well. So we can see Postgres' row estimate as well as what the actual rows are. The row estimates are slightly off. Postgres estimates there's 20,000 rows, but actually it's returning 40,000 rows. And when you're looking at explain plans, the row estimates are actually very important because they are, amongst other things, driving how Postgres decides which join type to use. So it's important that your row estimates are at least roughly directionally correct. Franck does a bunch of tests here, and he summarizes here in this table. So what we can see is that right now with the current data, without having analyze run, Postgres will estimate roughly the same amount of rows being returned for each of the different timestamps. And that's really because there are no statistics about this. Now, when we run analyze, Postgres will build these internal statistics that are stored for each column. And so now it's much more accurately being able to determine that for February 7th, we have about 40,000 rows, and this matches the actual amount of rows. That's how it's supposed to work, is that the planner is able to use these statistics to plan quickly from the cache data. Now, Franck does a few more tests. He's adding additional data on subsequent days. Without having to run analyze, Postgres will actually be able to estimate how many rows were added. And so in this case, it will actually assume that, on February 8th, we added more rows, and so they match the estimate. But then it also estimates that on February 9th, there's some data. And there is actually no rows added on this day, but Postgres doesn't have any precise estimates about this. And so what you can do to help Postgres understand what additional data might be available is when you create an index, Postgres is able to use the index as part of its planner estimation. And so you can see here, once we have an index on a timestamp column, Postgres is actually accurately able to predict that on February 9th, there's no data. And so the benefit here is as we add more data, Postgres is able to estimate the fact that there is more data coming in for these newer timestamps just by looking at the index and by being able to assess the shape of the table from the index's maximum value. Sometimes it's interesting to understand how this works behind the scenes. And of course, the good news is Postgres' source code is easily accessible, and these selectivity decisions, like how many rows are matching, are usually located in the cellfuncs.c file. So here we have different selectivity functions for different operators. Here in this case, we're doing a range comparison. We're saying this value larger than this fixed constant value. And so we can see here that Postgres uses the inequality histogram selectivity function to determine selectivity for such operators. Now, the important thing that we want to understand here is that sometimes Postgres will not just use the internal histograms that are stored in the statistics, but if Postgres determines that you're looking at the first or the last histogram of those internal statistics, then it's also looking at an index through the getActualVariableRange function. As the table is changing and you're adding more values at the tail ends of those histograms, Postgres wants to have a more accurate estimate. And so the idea is that only in certain conditions, the getActualVariableRange gets called for these inequality comparisons. Now, this has actually been a bit of a problem over the years. And so if you were using Postgres, let's say 6-7 years ago, you might have seen workloads where this becomes a bottleneck. And again, the problem is this gets called during planning. So this is not something that you would usually expect. Usually planning is fast, and you wouldn't expect planning to actually look at the actual table or actual indexes. So this is one of these rare cases where Postgres does do that. So as recently as 2022, Tom Lane committed a patch that improved the getActualVariableRange performance to avoid behavior around dead tuples. So the problem is if you have a lot of updates to your table, a lot of changes, a lot of deletes, then you will have dead index entries that get in the way of Postgres finding the actual maximum value through the index. And the challenge, of course, is this can make things really slow. And what I found interesting recently is that Mark Callaghan runs what he calls the insert benchmark, and he compares different database technologies, including Postgres, and he looks at performance regressions over time. Earlier in January, he had this post where he said, this is weird, I'm seeing a performance regression in Postgres 14. And recently, earlier this week, he said, hey, this wasn't actually performance regression. And so what's interesting is it's again coming back to this get actual variable range function. Even though he was on 14, what he was seeing was a regression because on Postgres 14, vacuum was changed to sometimes skip the index vacuum phase if it's not necessary, if only a small portion of the table changed. And so the way his insert benchmark was written, this triggered the get actual variable range function to be more expensive because the vacuum wasn't running on the same schedule that it was running on 13 and earlier. The fix here was to run vacuum explicitly with the index cleanup on argument. This will force vacuum to do an index cleanup even if vacuum on 14 plus would otherwise not do this. And so all in all, if you're running into a problem where suddenly your planning is slow and you know it's a table where there's lots of dead rows, I would encourage you to take a look at your vacuum schedule. And if it's your own self-managed server, it's also worth doing a perf top to understand if you might be running into a bottleneck with get actual variable range. But then again, this has been a problem of the past mostly. Since those recent improvements that Tom made, you will have one slow planning cycle, but then with subsequent planning, it's going to be able to reuse those benefits from the earlier planning that was slow. In recent times, this is not something that I've heard of much, but still it's good to know that this is one of the cases where the planner will look at the actual indexes as part of the planning process. Thank you so much for listening. This was 5 Minutes of Postgres. Subscribe to our YouTube channel to hear about next week's episode, and talk to you next week.